So for the fourth problem, a uniform rod PQ of length L is hinged at one end P. The rod is kept in a horizontal position by a massless string tied to a point Q. So that's why this is the PQ rod is here, and it is hinged at one end P. So it is hinged at one end P like this, and here it is Q is there, and it is tied to a string. So this is tied to a string, and this end can be taken as a Q here, and it is tied to a string. The rod is kept in the horizontal position by a massless string tied to a point Q. If the string is cut, the angular velocity of the rod after an angular displacement of 30 degrees is. So after an angular displacement of 30 degrees is. So here in this case, now this is uniform rod is there, and P, Q, and this string is there. If the string is cut, then what happens to that angular velocity when that angular displacement at that angular displacement of 30 degrees? So that 30 degrees position means it will be like this. At that 30 degrees position, that uniform rod will be like this. This can be taken 30 degrees here. Now in this case, the center of gravity of this rod is here. That center of gravity also rotates like this, and now it becomes the new position of that center of gravity will be like this. The new position of that center of gravity. So that's why when you are taking this separately, this will be taken like this. And now here it is H. This can be taken as the H. This can be taken H. So that's why here the first one, so it is H can be taken here. This is a theta general, that is a 30 degrees, and thereafter this becomes L by 2. If you are considering that uniform length of that is the uniform rod that you are given, it is the L. So that's why this becomes L by 2, and H is here and 30 degrees. And now here we have to apply that conservation of energy. Now when this string is cut, then it is losing potential energy. When it is coming down like this, it is losing potential energy. At the same time, it is gaining kinetic energy. So that's why loss of PE is equal to gain of KE. It is gain of KE. And one more point that you have to remember, it is not translational, it is not rolling, it is purely rotational, because it is rotating like this. So that's why loss of PE is equal to gain of KE. And loss of PE is nothing but it is mgh, because it has lost this much of height. So that's why mgh is here. And thereafter gain of KE, that is rotational kinetic energy. In that case, it is 1 by 2 I omega square is here. This is the equation from which we can determine this answer. So now it is mgh is equal to 1 by 2 I omega square, and h is to be determined separately because your answer is given in terms of that L only. H is not coming there. So for that we are taking that formula sin 30 is equal to it is h by L by 2 is here. So that's why 1 by 2 is equal to h by L by 2. So that becomes it is h is equal to, from that h can be determined. So now it is taken 2h by L is here, and h is equal to L by 4. H is equal to L by 4. So once again repeat, sin 30 is equal to opposite side by that hypotenuse h by L by 2. So it is the 2h by L, and our requirement is that is the h value. H value means it is L by 4. So that L by 4 is to be applied here. mg L by 4 is here, and it is 1 by 2 and I. It is moment of inertia. Moment of inertia of this thin uniform rod means it is rotating with respect to one end like this. It is rotating with respect to one end, for which we have to apply that formula I is equal to ml square by 3. I is equal to ml square by 3. So that's why it is ml square by 3 to be applied. Now here also it is given in terms of that L only. So ml square by 3, and thereafter omega square will be as usual. So m will be cancelled, and again one L also will be cancelled like this, and thereafter it becomes a 2, and that omega square is equal to you are taking 3z by 2L, and omega is equal to square root of 3z by 2L. So once again I repeat this question. So here slightly difficult is here in this area. So suppose if at all you are applying, if you are taking this L by 2 here, then you may apply that is a cos 30, but it is not correct, sin 30, because L by 2 is here. This portion cannot be the L by 2. You have to take the figure like this only. Now is a uniform rod, and it is the string is cut, it is rotating like this about n end, and after making an angular displacement of that 30 degrees, what is its angular velocity? Here we are applying the conservation of energy. Loss of P is equal to gain of Ke and mgh, and h is to be removed carefully, and here sin 30 is equal to h by L by 2, h by L by 2. So that's why here it is a h is there and L by 2 is here. So now it is from this figure it is clear L by 2 is coming here only, not here. So that's why L by 2 is coming here only. So from that it is a h is equal to L by 4. So when you are applying those values, you are getting that omega is equal to square root of 3g by 2L. Next one. Next problem, it is based on conservation of energy. So for that fifth problem, a body of radius r and mass m is rolling horizontally without slipping with speed v, then rolls up to a hill to a maximum height h is equal to 3v square by 4g. What is that body? What is that body? And here also this problem also based on that conservation of energy. Conservation of energy, a body of radius r and mass m is rolling horizontally without slipping with speed v. So like this. Now here it then rolls up a hill to a maximum height h is equal to 3v square by 4g, to a maximum height of 3v square by 4g. So first of all, we consider this rolling body is here, and to that maximum height it could rise to that height of, it is h is equal to 3v square by 4g is given, 3v square by 4g. Now what is that body? What is that body? So in this case, what is that body means here it is also conservation of energy. That conservation of energy means a total energy at this position, and again the total energy at this position. These two positions can be balanced. So first of all, total energy at the bottom of that inclined plane is purely, it is the rolling energy. It is rolling energy, for which you already know. So that is KER, KER at bottom of inclined plane, KER at bottom of inclined plane, and that will be equal to, that is equal to KER, that is the rolling kinetic energy at the bottom of the inclined plane. Here it has only that potential energy, that is equal to PE. It has only that potential energy, because on reaching this much of height, it is coming down to rest. So that's why it has purely that potential energy. In this case, now here it is the rolling body at the bottom of that inclined plane is, it is taken as half mv square, half mv square of 1 plus k square by r square, half mv square of 1 plus k square by r square, and thereafter PE is equal to mgh, that h value is already given to you, and that h is nothing but 3v square by 4g is given. So that's why it is m will be cancelled, and it is v square by 2 is there, and 1 plus k square by r square, and thereafter it is a small g, and in place of the h what we can apply, 3v square by 4g. It is a 3v square by 4g. Now here small g will be cancelled, and again v square is also cancelled, so it becomes 2. So that becomes, it is a 1 plus k square by r square. Here that remaining factor is only that 3 by 2. So 3 by 2 is here, and thereafter k square by r square is equal to, k square by r square is equal to 1 by 2. K square by r square is equal to 1 by 2. And from that what you can have, k square is equal to r square by 2. K square is equal to r square by 2. If at all it is multiplied on both sides by m, it becomes mk square is equal to mr square by 2. Mk square is the moment of inertia, general formula, and mr square by 2, for which that mr square by 2 is coming. For which that mr square by 2 is coming. That natural axis formula mr square by 2 is coming in two cases. The first one is, it is circular disk, and for that circular disk also about its natural axis, that formula is the mr square by 2. And similarly, when you are coming to this solid cylinder, and that solid cylinder also about the natural axis, again it is the mr square by 2. So that's why here the options are, two options are correct answers. So one is a disk is there, and the second one is a solid cylinder. That is A and D are correct answers. So that is a disk is here, and thereafter that is solid cylinder, solid cylinder. So these two answers are correct answers. So it is a simple application of conservation of energy. So here in this case, that is a rolling kinetic energy at the bottom of the inclined plane is equal to that potential energy of mv square of 1 plus k square by r square is equal to mgh. In place of the h, we apply this value. After cancelling, you are getting that k square value as r square by 2, multiplying it on both sides by m. It will be I is equal to mr square by 2, and that is coming in both cases. That is two cases. That is the disk is here and the second one is solid cylinder. So this problem is also over. Now we are coming to this next problem. So here in this next problem, you are given a halo and a solid spheres have equal mass and equal radius also. They are revolving at equal angular speed. If they are stopped by equal torque, then which one will make more revolutions before coming to rest? Which one will make more revolutions before coming to rest? So it is just similar to that of the problem which is coming in translatory motion, but in that case you are having, instead of that halo and solid sphere, you are having that car and lorry. Suppose a car in a translatory motion, I give some example like this. A car and lorry are moving with the same velocity and they are subjected to same retarding force. When they are subject to the same retarding force or the braking force, then they are coming down to rest finally. Then which travels shorter distance, that is which travels a shorter distance before coming to rest. In that case, what we have taken, that is a car is there, and thereafter it is lorry is taken like this. So car and lorry, they are moving with the same velocity. Here in this case, you are given they are moving with the same angular speed. They are stopped by equal torque. There it is, they are stopped by equal braking force. Then which travels a shorter distance or the more distance before coming to rest. So in that case also, what we are taking, it is a W is equal to half mv square is there. W is equal to Fs, that is a general formula. W is equal to Fs is there. And W is equal to Ke, that is nothing but half mv square is here. Half mv square is here. From 1 and 2, we can balance that Fs is equal to half mv square. Now here F is already constant. F is already constant. Why? Because already you are mentioned they are stopped by a same retarding force. So that's why here F is a constant, and thereafter they are moving with the same velocity. V is constant. So F comma V are constants. So because of that reason, what we have to take, that is M proportional to S. M proportional to S means the body which has less mass travels less distance before coming to rest. So it is directly proportional. So that's why the body which has less mass comes to rest, that is comes to rest after traveling a shorter distance. So that's why car comes to rest after traveling. Car travels a shorter distance. Car travels shorter distance. Shorter distance. And here lorry travels more distance. Like this. This is answer. So the same concept we can apply in this present problem also. In this present problem also, here also, now you are given a halo and a solid sphere, just like that is a car and again that lorry, and here also have equal mass and equal radius, and they are revolving at equal angular speed, and if they are stopped by equal torque. So like this only we have to take that W is equal to tau theta. W is equal to tau theta is here, and this is taken as the first equation. This is taken as the first equation, and thereafter W is equal to Ke. So that is taken as 1 by 2 I omega square. So it is taken 1 by 2 I omega square is here, and now here they are stopped by equal torque. So in this case, now this is taken, it is the tau theta is equal to 1 by 2 I omega square is here. Tau theta is equal to 1 by 2 I omega square. And here what are constants? There in that previous case, that is F and V are constants. Now here tau and omega are constants. So that's why here tau and again the omega are constants. Its meaning is that is I proportional to theta. Now it is I S. because you are given it is a hollow sphere and again the solid sphere. So that's why IS and again IH is equal to theta S by theta H is here. And IS is equal to, already you know, it is nothing but 2 by 5. Solid sphere, it will be the 2 by 5 is here. So 2 by 5, and thereafter for the hollow sphere, it will be 2 by 3, and it is a theta S by theta H. Now 2 by 5 and again into 3 by 2. So 2 by 5 and it is the 3 by 2. So now it will be 2 will be cancelled. So it will be the 3 by 5 only. So it is a 3 by 5 is equal to theta S by theta H. That indicates a hollow sphere that makes a more number of revolutions before coming to rest. Hollow sphere that makes a more number of revolutions before coming to rest. So just I will continue, I will once again tell you this problem. So this given problem can be compared to that of the problem which is coming in this translatory motion. In that translatory motion, you are given it is a car and a lorry, and which comes to rest in a shorter distance for the same application of that braking force. In that case, we have taken these formulae, and Fs is equal to half mv square. Ultimately, this is the car travels a shorter distance like this, and a lorry. And here it is a W is equal to tau theta, W is equal to 1 by 2 I omega square. Now here tau and omega are constants, and here it is tau and omega are constant, I proportional to theta, Is by S is equal to theta S by, and here it will be 3 by 5. Its meaning is that is which one will make more revolutions before coming to rest means that is the hollow sphere. So thank you. Thank you. We can continue in the next class.